Hello everyone, welcome back. I'm not sure if Nathan will be joining us today, so I am going to be recording this lecture for us. He'll be able to watch it later, and you two will also be able to watch it later as well on the YouTube channel. So first and foremost, happy 2021, I should say. Hope it's been a good year so far for you. For me, it's been really great. I'm ready to just move on from what a crazy year 2020 was. And by the way, I'm dealing with some really bad allergies. So if I sound congested, not quite sounding myself, that would be why. I'm going through a pretty severe allergy attack at the moment. So let's press on then, shall we? We are going to be talking about improper integrals. So throughout this class, I constantly refer to this calculus class in particular, as having three main ideas. The first one being derivatives, the second one being integrals, and then the third one being infinite series. So you wouldn't think that something like sequences and series would be a calculus topic, but it actually is. So we're not going to really get into that much today, but I want to give you guys a preview to what that really is, about what infinite series can do in a calculus context. So we know what series are. We know what series and sequences are. So this is a series, but let's actually just start with a sequence. Let's say we have some sequence. I'm going to call it A. Let's say it is start with 1, and then 2, and then 4, and then 8, 16, 32, and so on. So we can probably easily identify what the pattern is. We can tell what rule we have to use to go from one element to the next. So we're going from 1 to 2 to 4 to 8, and then so on. We can tell that we're just doubling every time. So a sub n would be equal to 2 times a sub n minus 1. So for example, if we pick the fourth element and we want to find the fifth element, n would be 5, n minus 1 would be 4. So the this sequence at the index of 5, it would be twice the previous one. That'd be twice 8. So that's just the general algebraic rule we use to go from one sequence element to the next sequence element. These are all elements. So 1, 2, 3, 4. Sorry, not 3. Got ahead of myself there. 1, 2, 4, 8, 16, and 32. These are all sequence elements. And then the smaller numbers below, 1, 2, 3, 4, and 5, I consider these to be indices. Individually, each of them is an index. Altogether, they're collectively known as indices. So a sequence has indices, and it has an element for every index. That's the main idea of a sequence. So let's review what a series is. So it's really similar to the concept of a sequence. A series is what you get when you add together a finite number of elements from a sequence. It could be something like this: I equals 1 to, I don't know, let's say 4, or maybe 5, why not? So the difference between a series and a sequence is that the series adds together all the terms, or not all the terms, a finite number of terms in a sequence. So in this one, it's saying we're going to start at 1, add them all together until we get to the index of 5. So our starting index is going to be 1. The element at index 1 is going to be 1. And then we're going to add together the element at index 2, which is 2, plus the element at index 3, which is going to be 4, plus the element at index 5, index 4, which is going to be 8. And then plus the element at index 5. This is where we're going to stop. We always start at the number at the top. And by the way, this right here, this is a capital Greek letter sigma. Sigma just means the sum of something. Whenever you see the symbol in math, just automatically think of the sum. That's what it's trying to do. That's what the symbol represents. It's a sum. So we're going to take the sum of everything starting at 1 and then ending at 5. So we started with an index of 1. We have an index of 2, index of 3, index of 4. And then we're going to add together just one final element. We're going to add together the element at the endpoint of 5. So the element at an index of 5 would be 16. So that's the main idea of sequences and series. So up to this point, I don't know if you guys have seen that many series, maybe in Algebra 2, maybe in pre-calc. My understanding is they don't really get into this stuff that much anymore. When I took Algebra 2, I took Algebra 2 honors, and then I never actually took pre-calc. I kind of just studied pre-calc independently. And both of those classes that I studied went into sequences and series. So if you guys aren't too familiar with this, when we start getting really, really into this, don't worry. We're going to be covering this a lot. We're going to be making sure we're all set on the basics before we start applying this to calculus and applying calculus tools to this concept. So just one more thing. So I want to give you guys a preview of what we're going to be doing when we start getting really into this in a calculus context. So we're still going to start at a finite endpoint, but we're actually going to go to infinity. Instead of adding together a finite number of elements, so for example, in this one we added together 5 elements. We started at 1 and stopped at 5. For something like this, we're actually going to add an infinite number of elements. It sounds crazy and weird and impossible, but it can be done. I don't want to spoil the surprise for you guys, so we're going to be getting into this maybe at the end of this week, maybe next week. Infinite series. So the topic we're going to be covering today provides kind of, I feel like it's a nice segue into the concept of infinite series. We're going to be discussing improper integrals, and that will help us prime our minds to have a better understanding of infinite series when we get to this point. I consider improper integrals to kind of be the midpoint between integrals and infinite series. It's one thing that kind of ties them together. So I felt like it was a good idea to start with this. So what is an improper integral? Well, we know what integrals are. We've done many, many, many integrals in this class, but what the heck is an improper integral? An improper integral is similar to an infinite series. We have an integral with a finite endpoint, but has some indeterminate alternate endpoint. So for example, we could take the integral of some function starting at 1, going to infinity. And this seems like a really weird concept. We know the integral is an area under a curve. So how the heck does it make sense to have a definite answer for an interval that never ever ends? X just keeps going on and on and on forever. How the heck does that make sense? Well, in our old way of thinking, it actually does not make much sense at all. So we're going to introduce some new tools, some new conventions to help us make sense of this really kind of weird and foreign topic that we're starting for the first time. So I'm not going to give a specific function. I'm just going to generalize it. So for some cases, it's possible to find this integral. In other cases, it's impossible to find this integral. So before we talk about how to solve an integral of this kind, we have to talk about the concept of convergence and divergence. Convergence and divergence. So I want to hear from both of you guys in the chat. Have you guys heard of either of these words before? Convergence or divergence? Let me know. If you're not too sure, just say I don't know. But if you've heard of any of these words and you want to take a crack at what you think they mean based on context, it doesn't even have to be math related. It could be any definition of convergence and divergence based on things you've encountered in your daily life, based on context clues you might have seen elsewhere. So I'd like to hear from both of you guys, just some guesses on what you think either of these two words might mean. And like I said, it's okay to just type I don't know if you're not too sure, but I would like a guess. Perfect. That's a really excellent answer. Convergence can be thought of as things coming together, and divergence can be thought of as things going apart. Thank you for that answer. That's perfect. And that actually applies, that very same definition applies to a calculus context as well. So let's define the concept of convergence. There is a rigorous definition for convergence. So we're going to have to approach this using the concept of a limit. A limit is going to be a tool we use to understand this concept a little bit better. So we can write this integral. Whoops, wrong tool right there. We can write this integral as the limit as alpha, Greek letter alpha, goes to infinity, of the integral 1 to alpha and then f of x dx. So the rigorous definition of convergence is if this limit exists, then the function converges, the integral converges. An improper integral converges. It converges if this limit exists. So if the limit exists, it converges. If the limit does not exist, the integral diverges. Convergence, divergence. So one important thing to note is that it is impossible to take this integral if it diverges. We can only take an improper integral that converges. So that's one thing to keep in mind. We're going to have to do a convergence test for one of these integrals before we can actually apply it, because the limit is going to tell us if we can actually integrate or not. So let's start with an example. Here is a classic example. I think every calculus class probably starts with this example. So we're going to take the integral going from 1 to infinity of 1 over x squared dx. So before we can integrate this, we have to see if we can integrate. We have to see if it's actually possible to integrate this thing. So we have to see if the limit exists. So this can be written as the limit as Greek letter alpha goes to infinity. And then we're integrating from 1 to alpha of f of x dx. So let's see if we can prove if this thing converges or not. Let's see if the limit exists. So we're going to replace f of x with just 1 over x squared. That is our literal definition of f of x in these circumstances. So let's see what happens if we take the limit of this function. Let's forget about calculus for now. Let's just focus on the limit part of this. So let's say we write this a little bit differently. Let's say we have the limit as x goes to infinity of 1 over x squared. So let's see if this limit exists, shall we? Let's see if this limit exists. So I feel like one of the most effective ways to test that would be to graph it and then see what information we can get from the graph. So I'll share my screen in just a moment. All right, here we go. So I just drew the function. We want to see what happens if we try to take x to be infinitely large. We just keep taking larger and larger values of x. We want to see if the limit exists. So let's review what it means for a limit to exist. So if we have something like this, natural log of x, for instance, we can tell that there's no asymptote. Natural log of x only has a vertical asymptote. There's no horizontal asymptote. So a natural log of x, it will keep going on and on and on forever, and y will continue to increase without bound. For some functions with an asymptote, you can clearly see that the y starts increasing less and less and less, and it kind of flattens out towards the horizontal, but natural log of x does not do that for us. Natural log of x just keeps increasing over and over and over without bound. So this one, the limit would not exist of natural log of x if we took the limit as x approaches infinity. But this one, I think it actually does converge. So let's take larger and larger values of x and then see what the y gets us. So y is 2, and then y keeps dropping down to smaller and smaller values. So theoretically, if we asked ourselves, if x could theoretically reach infinity, what value would y reach? We can tell that y would have to be 0. If x were to eventually reach infinity, theoretically y would reach 0. So that's a big indication that we know the limit exists because this equals 0. Let's go back to the whiteboard. So the limit does exist. We found out that the limit is equal to 0. So the limit does exist. We are able to actually integrate this now. So we have 1 over x squared. Let's see if we can integrate this. So it'll be helpful if we could rewrite this, maybe make this just x to the negative second power. So what we're going to do is we're going to add 1 to this exponent. So if we add a 1 to negative 2, we're going to get -1. And then we're going to divide by the result. The result's -1. We're going to divide by -1. So we're going to get something like this. Limit as alpha goes to infinity of the antiderivative. So that would turn out to be x to the -1st power divided by -1. So we have, or sorry, I got a bit ahead of myself there. So x to the -1 power, x to the -1st power would be 1 over x. So this is going to be -1 over x. Going from 1 to infinity, 1 to alpha, sorry. Going from 1 to alpha. So we can move the negative out front. So this would be equal to -1 times 1 over x. Going from 1 to infinity. So this would be -1 over infinity minus 1 over the other endpoint, which is 1. So this would be 1 minus 1, 1 over 1, excuse me. So we know from looking at the previous example that 1 over infinity converges. That just becomes 0. So this whole thing goes to 0. And then we have -0 minus 1 over 1 is just 1. So we're going to distribute the negative. We're going to have -0 minus -1, which would just be 0 plus 1. So the answer to this problem is 1. So let's go back to the graph and try to interpret that and see what this really means. So this result tells us that if we start at x equals 1, if we start at x equals 1 and we take the area under the curve, all of this area right here, going from x is 1 all the way to x is infinity, if we were to take all the area all the way up to x is infinity, this would have an area of 1. And this is one of the most beautiful things about math. There are many different hidden connections to other parts of math and to nature itself. It works in many beautiful and unexpected ways. So for example, you would think that something like this would have some weird, nasty decimal, maybe some roots in there, maybe something in terms of pi. But this is actually just going to be a whole number, one of the most known whole numbers of all time. This is just going to be 1. So that's one of the most beautiful things about math. You'd think it would be some nasty decimal, but it's just 1. The area under the curve from this point all the way to the end is just 1. I don't know about you guys, but my mind is blown by this. So let's maybe do some more examples. And of course, please stop me at any time if you have questions about anything at all. Let's find another problem to do. All right, let's try something a little more advanced. Let's try the integral going from -infinity to positive infinity of x times e to the -x squared dx. So we're going to do what we did last time. We have to verify that this actually exists. So one thing we're going to notice right away is that it goes from -infinity to infinity. So we have 2 indeterminate endpoints instead of just 1 like we had in the last example. So we're going to have to do something a little bit different for this one. So our limit tools don't really work very well when we have 2 different limits in the same integral to work on. So we're going to break it up into 2 separate integrals. So this is the area going from -infinity all the way up to infinity. So I'm going to rewrite this as 2 separate integrals. I'm going to make the first one the integral of -infinity up to 0 of our function, oops, messed up, e to the -x squared. And then we're going to add the integral going from 0 up to infinity. So we're just breaking it up into two. We're going to have a midpoint of 0. We have a stopping point of 0. We're just going to do one integral from negative infinity to 0, and then one from 0 to positive infinity of the same function. And by the way, if I randomly go on mute, it's because I'm having an allergy attack. So fair warning, that's what's going on. Don't be alarmed. So we're going to start by maybe taking the limit of the first one. So let's see if this is possible. We're going to take the limit as alpha approaches infinity of the integral going from, this is actually going to be alpha on the bottom, to 0. And then let's see if this exists. Negative infinity is what I meant to say, what I meant to write there. So I want to go to Desmos and graph this the way I did the last one. See if the limit exists before we try to integrate. X times e to the negative x squared. So once again, I want to share my screen with you guys. So it looks like they both exist. So this is the function we're interested in. It looks like it converges in both directions, because if we take smaller and smaller values of x that approach negative infinity, we can tell that y approaches 0 as x approaches negative infinity. So the leftmost limit exists. Now let's do the same thing on the right side. So let's take larger and larger values of x and see what happens to y as x gets unboundingly large. So y would also approach 0 as x approaches infinity. So the limit exists in both cases, so that's the green light we need to go ahead and start integrating this. Both limits exist, both integrals exist, they both converge. We have the limit as alpha approaches negative infinity. And then for this one, we want to probably use U substitution because we have an x squared and we have an x on the outside. An interesting thing to note about this is that without the x being there, this is impossible to integrate. This has no elementary antiderivative. Even Wolfram Alpha or a graphing calculator can't integrate this. So we have to have the x there in order for there to actually be an antiderivative. So we're going to set u equal to negative x squared. We're going to set du to be, this would be negative 2x times dx. So if we look at the integral, we have the dx, but we don't have a negative 2. So I'm going to divide both sides of this differential equation by negative 2. We're going to have negative 1/2 du equals 1 times dx. So let's go ahead and start substituting in. I'm going to make the negative 1/2 go out to the front of the integral. And then we're going to make this into, this would be, I think I made a mistake in the u substitution part. So the antiderivative would not just be 2, it would actually be 2x. Sorry about that. Negative x squared, and then the derivative of that would be negative 2x dx. That's better. Now it's looking a little more right. X dx, perfect. So we have an x and we have a dx, and then we have all of that times e to the u. So this would be 1/2 du times e to the u, negative 1/2 du times e to the u. So we already have the negative 1/2. We're just missing the e to the u and the du. So we're going to have e to the u times du. And then the next one is actually going to be identical, but this time it's going to be a different limit. This would be the limit as alpha approaches positive infinity. We're going from 0 to alpha of the very same function. The u substitution works exactly the same. So we're going to use the same u and the same du that the other integral used because they're the exact same function. We can reuse these things. Negative 1/2 e to the u du. And then from there, we have just the integral of e to the u. So the antiderivative of the e to the x or e to the u is going to be the same thing. So the antiderivative of e to the u is e to the u. So we have negative 1/2 times the limit as alpha goes to negative infinity of e to the u. And u is going to be, we set u equal to negative x squared. E to the negative x squared going from alpha to 0. And then we have another one. We have negative 1/2 times the limit as alpha goes this time to positive infinity of e to the u. So that would be e to the negative x squared going from 0 to alpha. Don't need this stuff anymore. So let's see what happens as we do e to the negative 0 to the second power, because that's what's really going on here. We're going to have e to the negative 0 to the second. And then we're going to subtract e to the negative infinity, essentially, to the second power. And then something similar goes on in the other integral. We have negative 1/2 integral e to the negative, this is going to be, in this case, alpha is positive infinity. Why do I keep forgetting the negative sign? This is supposed to be negative infinity squared. That's better. And then this one should be positive infinity squared. So we have negative infinity squared. Oh, and then minus e to the negative 0 squared. So negative 0 to the second power is just going to be 0. So this is just going to be e to the 0 power, which is just going to be 1. We have negative 1/2 times 1. And then we have negative infinity to the second power. So we're going to do the exponent first. Infinity squared is just as unattainable as infinity. They both signify going infinitely large, so the square doesn't really have an effect on this at all. So we have negative infinity. And we know from looking at the graph, as x approaches negative infinity, y would approach 0. So this entire thing in the second set of parentheses has a value of just 0, so we have 1 minus 0. And then over here, we have, this will be the same thing over here. So this would be e to the negative infinity. That would be a 0. And then this one would be e to the negative 0 squared. 0 squared is just going to be 0. So then e to the 0 is going to be 1. So we have 0 minus 1. So then let's simplify. So we have negative infinity, or sorry, negative 1/2. I don't know where that came from. Negative 1/2 times essentially just 1. And then we have minus 1/2 to the 0 minus 1. So this would be negative 1/2 times negative 1. So that would just end up being positive 1/2. So we're going to add 1/2 and we get 0. So you might think, oh no, we did something wrong. We're trying to find the area under the curve. We're not supposed to get 0. If we take another look at the graph, clearly the area is not 0. Clearly we do have a discernible area. We have some under this part of the graph. We have a little more under this part of the graph. So how the heck does it make sense that our area is 0? Did I make a mistake? No, it turns out that it actually does make sense, because remember from the net change theorem in calculus when we first started talking about integrals, that whenever we have a situation like this where they are symmetric about a certain axis, so all the area to the right of the y-axis is equal to all the area to the left. So we consider this to be a negative area to the left. We consider this to be a positive area to the right, which means they are equal in opposite areas, which means they cancel out. They add up to a total of 0. So if we wanted to fine tune this and find the actual area, we would have to take whatever appears to the left of the y-axis. We would have to take the absolute value of that area in order to find the true area. Because what we did just now on the whiteboard, we didn't find the area under the curve. Sure, we found the integral, but that's not the same thing as the area under the curve. So let's do a quick modification, see if we can find the actual area, because 0 is not it. So we know that one of them had an area of -1/2. We know that the other one had an area of 1. So like I said a few seconds ago, in order to make a change, in order to make this not just the integral, but the area under the curve, we have to take the absolute value of the negative portion of the graph. Take the absolute value of the portion of the graph that returns a negative area. So that would be this part right here. So the -1/2 corresponds to the area to the left of the y-axis. +1/2 corresponds to the area to the right of the y-axis. So I want to take the absolute value of whatever appears to the left of the y-axis. So area would not be -1/2 plus 1/2. It would be +1/2 plus 1/2, and we get 1. So the area under the curve going from -infinity up to +infinity is 1. And that's totally mind-blowing. Before taking this class today, we didn't think it would be possible to take an infinite area. We would think, well, because x just keeps getting larger and larger, the area should keep getting larger, right? How does the area end? And that's where convergence is necessary. It only essentially ends if we can prove definitively that it converges. So in this case, the left side and the right side, they both converge to 0. But let's try something a little bit different and see if we can draw some more parallels between this and other graphs and other intervals on those graphs. So let's go back to the graph. Now I want to make a slight modification to this. I want to add 1 to the function and see if we can take the area. So without the 1 there, the area does exist. We can tell that x gets larger and larger and larger, y approaches 0. And if x gets less and less and less, y also approaches 0. So it kind of cuts things off. It looks like it goes on forever, but according to the rigorous definition of a limit, it actually stops at infinity. So the area looks infinite, but the area is actually finite if we look at things from a limit standpoint. So they both converge because they both reach 0. Now let's make this modification. So I want to hear from you guys. Do you guys think this will converge? Do you think the area under the curve, the integral, would exist for this function with the +1? Or would it diverge? I want to hear from both of you guys in the chat if you think it's possible to find this area under the curve. All right, thank you for your answer, Lynn. Let's see if Hannah also has an answer. So Hannah might be having internet connection issues. I know I am. I got that message from Zoom telling me that my connection is unstable. So there's a chance that I might go offline for a bit. Let me know if you guys can't hear me, because that just means my internet's not working very well. So let's talk about this real quick. Let's talk about convergence and divergence. So without the one, we know that they both reach zero, so the area is finite. It pinches off, and then the area all stops. Let's see if we add one, though. It doesn't ever pinch off. It doesn't ever reach zero. It just keeps staying at one forever and ever and ever. So that means we're going to add one. We're going to add another one. For every increase in x value of one, we're going to add one to the area. So we're going to be continuously adding one to the area for every value of x that increases. So that's how we know that this does not converge, because the area keeps going on and on forever. So the limit has to exist, and it has to converge to zero in order for the integral to exist. So this does not reach zero. It just stays at one. So the area never ends. The area just keeps going, adding one forever and ever. So this diverges. This converges. So that's a major idea of this topic. For it to converge, for the integral to exist, for the limit to exist, the integral in question has to converge to zero. It can't converge to one, can't converge to two, or any other number besides zero. So it only exists if it converges to zero. So let's go back to the whiteboard. Let's try some more improper integral problems. Let's try this one. We have the integral going from -2 to infinity of sine of x dx. And oops, I erased the definition of an improper integral. I'm going to write that again. In this case, it would be -2 to alpha, any function f of x dx. I can't spell, apparently. We already knew that, though. Exists IFF, if and only if we converge to zero, only if the limit converges to zero. If the limit exists and it converges to zero. So I'll say, actually, the integral exists if and only if the limit of f of x equals zero. It has to converge to zero. It can't go to 1 or 2 or any number besides zero. So I want you guys to take a few minutes, see if you can, for the first part, see if you can tell if it converges or not. And then if it does converge, see if you can find the value of this. So take a few minutes, see what kind of progress you're able to make, and let me know if you'd like a little bit of help if you have any questions. I feel my allergies coming on right now, so excuse me for a few seconds, maybe a few minutes. All right, really sorry about that, guys. Have no idea where these allergies are coming from, but they're driving me crazy. So are you guys doing all right still? You guys have any questions about anything? If you don't have questions, I want to maybe just give you guys a few more minutes, and then we'll go over this one together as a class. All right, so I think now we should go over this together as a class. So we know that we have one finite endpoint. It is x is -2. The sine function definitely does exist at this endpoint, but then we want to see if it converges before we continue. So sine of x, and in fact, all 6 of the trig functions are periodic, which means that they repeat. They don't steadily increase or steadily decrease. An interval contains both increasing and decreasing behavior. So this one does not converge. This one diverges. And the reason why it diverges is because it doesn't ever end. So if this part right here, if this section of the graph has an area of A, this one would also have an area of A. Yeah, sure, it's beneath the x-axis, but if we consider only the absolute value of this area, it would also have an area of A. In fact, all of these sections will. So that means the more we add to the x interval, the more we add to the interval, the farther we go right, the larger the area becomes. The area just keeps getting larger and larger and larger without ever slowing down. The rate of increase of the area never slows at all. It just keeps adding this area time and time again, so this one does not converge. For that being said, we cannot find the integral at all. It does not converge. The limit does not exist. We can't integrate it. But let's talk about a quick situation in which it would converge. See if we can make a simple modification to make this converge and then integrate it. So for example, if we had something like this, what if we had sine of x over x? And you might be wondering, what's the point of that? Well, the reason we want to look at this one is because we know that x is going to get larger and larger and larger. So we want to ask ourselves, what happens to the value of this function as x gets increasingly large? So sine of x is not going to change. As you guys both know, sine of x continues to oscillate between -1 and +1, on and on and on forever to infinity. But this denominator increases, which decreases the overall value. So as x gets larger and larger, this entire function gets smaller and smaller and smaller. So it would look something kind of like this. I know I'm a horrible artist. Clearly, I flunked out of art school. So we can see that the amplitude of each of these curves gets less and less. The amplitudes are decreasing as x increases. So this one actually does converge. This one, we can tell that as x gets larger and larger and larger, each of these magnitudes will continue to decrease until they both just eventually reach 0. They just become 1 with 0 eventually. So this one does converge, but unfortunately, we don't quite have enough time to integrate this. The thing about problems like this, with there being a limit, but with there being the fact that we have to prove that they converge and then actually integrate if they do converge, there is more work than a typical integral. So that being said, 4 minutes isn't really enough time to successfully work through one of these. So I'm going to let you guys go a few minutes early. So keep an eye on the YouTube channel. I'll be posting this on YouTube later this evening. So if you want to review this, it will be there. So hope you guys have a wonderful evening. Hope you guys have had a super awesome 2021 so far. And I will see you on Thursday. Have a good night, guys. Take care.